ADTs can encode several variants of the same type, more or less like subtyping or subclassing. They can also encode enums. They can also encode recursive data types. And finally, they can encode standard business objects. One of the many aspects that you need to learn when you are learning functional programming are ADTs. But what are they and why do we care so much about them? ADT stands for algebraic data types. They are a way to define complex data types. If you come from object-oriented programming, the closest thing that you will have there are classes. Let's start with the basics, the definition. We define an ADT by declaring its name and its variants. The variants might be parameterized or not. So let's consider a simple ADT where the variants are not parameterized. We start by declaring its name using the enum keyword. And then we define the two variants, true and false. You might think that I just tricked you, as this looks a lot like a Java enumeration. And it's true. However, this is different. In Scala 3, enums are just syntax sugar. So what lies behind it is much more complex. Now let's consider a slightly more complex ADT. This time we are considering an ADT where one of the variants has parameters and it's also recursive. That means that it uses itself in its definition. The classic example for an ADT like that are Peano definition of the natural numbers. So let's define them. We use the enum keyword and define the nat type. The first case is 0, and the second case is the successor of 0. It takes one parameter of type nat. Again, now we can define values of the natural numbers. We need to import our nat ADT to use it. And now we can define 0 is of course 0, or we can define 3, that is the successor of the successor of the successor of 0. And now we save and it compiles and we see that 3 is a natural number and 0 is a natural number. ADTs can also have type parameters. Type parameters enable to build generic recursive structures such as lists, trees, etc. So let's try to do one here. We use the enum keyword and we will define a list, my list. The type parameter is a, and now the first case of my list is the empty list. Let's call it empty, and the constructor, let's call it cons, and it takes the head of type A and the tail of type my list of A. Now we have a list, and let's try to construct some elements of this list. Let's build, for example, we import first my list into the scope, and now let's define an empty list. Would be just empty, or a list with one element of type nat. That would be cons, for example, 0 and empty. Or we can also use whatever native types that are available in Scala. For example, we can build a list of string. Test. And we save. And you can see here two things that are important. First, that we don't need to write the types of the type parameter. It is inferred by the compiler. And something you might notice is that this little plus here. This little plus here is used because the A type in this ADT is covariant. That means that a list of A is a subtype of a list of B if A is a subtype of B. So this means that, for example, we can have the empty, that is a list of type, in this case of type nothing, because nothing is a subtype of everything. And for example, we can check here that my list is of type nothing. But it also works with one list of type nat and one list of type string, because as we said, the empty type is of type nothing, which is a subtype of everything. And that's what the little plus here does. Finally, ADTs can also be used to encode standard business objects. Let me show you how to do this. I will create an ADT to represent a classic product in a catalog. So the first thing I will do is I will create an ADT for the amount, and it will have the amount can be in the price, but even better. The price will be in USD, and it has a price P double, and it can be in euro, and it can be also double. As you have noticed here, we have twice this P, so we can improve that, and ADTs can also have parameter, the main type, so we can say this P double, move it here, and now we need to tell the ADT how to initialize that, so this is a price of P. And the same goes for this one, price of P. Now we will create another ADT, and this time this will be for the quantity of our product, so quantity Q. We will use the same trick here, and this time we can have maybe a simple unit as the price, as the quantity. Unit Q is an integer, extends quantity Q, and case box. Let's say you have a quantity of boxes, extends quantity Q. And now let's create the product. So in this first part, I will create it using the enum construct as we have been seeing all the time, but there is a better way to do this, just for the future. So let's create the product. So we will create our product, and it will have one concrete product of type. It will have a code of type int, a description of type string, and it will have a price P, price, and a quantity Q. Let's save it. It works. And how do we create this? First, we need to import the price. We need to import the quantity, and we need to import the product itself. So now we create the product P1. It's a concrete product with the code 1, description, my nice product, and it has a price in USD, like 4 USD, and a quantity, like the unit is 3. And we create, it will compile, and now we see that we have created this concrete product of type product. So now you see how you can use ADTs to encode standard business objects. So until now we have seen that ADTs can encode several variants of the same type, more or less like subtyping or subclassing. They can also encode enums. They can also encode recursive data types. And finally, they can encode standard business objects. That's all I have for today. Thanks a lot for watching this video. If you arrived at this point, please subscribe to my mailing list where you can learn each time I publish a video or a blog post using the link in the description. You can also subscribe to this YouTube channel by clicking on the subscribe button below. And thanks a lot for watching and see you soon.